with Jeff Kohlberg at Cal State University Long Beach, and he's going to give us a demo of how he uses the Jmol manual in his class. And take it away, Jeff.
Okay, studying protein and nucleic acid structure with Jmol is a series of self-guided exercises by which students can learn about macromolecular structure. They learn how to use the program Jmol. When the crystal structure or NR structure of a protein is determined, the three-dimensional coordinates of the atoms are deposited in a structure file in the protein data bank, or PDB. Biologists can download these files and display protein structures with molecular programs like Jmol. Manual starts out with simple protein structures and leads to explore fibrous proteins, cellular proteins with multiple domains and multiple polypeptide chains, hemoglobin, enzymes, membrane proteins, and eventually large complexes like the electron transport system, mitochondria, and chloroplast. It allows students to explore the structures of A, B, and Z DNA, transfer RNA, and ribosomes. Let's go through a few examples of what the students will see on their computer screens as they go through these exercises. First, go to the website of the PB and type in the ID number of the file that they want to download. The structure has an ID of 1AL1, so let's type that in. And this page is a PDB summary page with lots of useful information about the protein. In the course of doing the exercises, students learn how to understand the information on this. Downloading is done with this file menu. Now we go to the program Jmol, and I go to my downloads file. In the file 1AL1. This is of an amphipathic alpha helix. The cartoon display is what the students will see initially. They can rotate the molecule with their mouse, or if they hold down the Shift key, they can zoom in and out with the mouse. They double-click and drag. They can translate the molecule. They can control the appearance of the molecule by right-clicking or control-clicking on it. And they set the cell scheme to see, say, CPK space fill. They get this representation of the molecule. So, scheme 6 gives you representation. Now, scheme Y frame gives the same thing except with thinner bonds. Scheme shows you the backbone atoms, a trace connecting the backbone atoms. And scheme shows both the atoms and the bonds in CPK colors. It's easier to do this by typing commands into the script console. The students gradually learn the script language as they go through the exercises. So if I type space fill, then I see a space fill representation. I can actually get the rotating, on, and I can rotation by typing spin off. I can use one other type of representation, a backbone representation connecting the carbon atoms, and I can make that thicker by typing backbone 100. Here's an alpha helix. Here, looking down the axis of the alpha helix, and it's easy for the students to see the 3.6 amino acids per turn of an alpha helix. If I go to the style scheme, now I can type other commands. I say select, pick green, and that takes all the nonpolar amino acids, colors in green. Select positive or yellow. Negative color magenta. And now you can see the amphipathic alpha helix with the nonpolar amino acids on one face and the charged amino acids on the other if I select backbone and CPK colors, only the side chains are coded according to their polarity. Gives the students an appreciation of what this looks like in 3 dimensions. The epipathic alpha helix with one nonpolar face and one polar face. I can restore the original view by typing undo. So take a look at another molecule. Actually is the second one that the students will see. The immunoglobulin G domain of streptococcal protein G. This molecule has a number of water molecules in the crystal structure. We can get rid of them by typing delete water. Here we see the alpha helix and the beta pleated sheets. I can put this in backbone representation. Now you can clearly see the course of the polypeptide chain. In this, the alpha helix is magenta and the beta pleated sheets are yellow. But if I type group, I have a trace where the chain starts with cool colors at the amino terminus through warm colors at the C terminus. And you can see clearly that the alpha helix is in the middle of the primary structure. We can return the structure-based theme by typing undo. Now we can visualize the hydrogen bonds by typing H bonds calculate and show the hydrogen bonds in the molecule and adjust them so that they connect atoms to the backbone display. You can see all this more clearly. I make the hydrogen bonds thicker and change the backbone, the background, to white. We can see this more clearly. And now the students can see the hydrogen bonds connect the atoms of the beta pleated and of the alpha helix. You click on atom, then the identity of the atom and the amino acid residue is displayed in the script console. Let's take a look at what the students will see with the oxyhemoglobin. Let's get rid of water. Color polypeptide chain. This shows the 4 chains of the hemoglobin tetramer. Now the oxyhemoglobin binds 2,3-bisphosphoglycerate and is left between the beta chains. In this structure, we have a molecule of inositol hexaphosphate in the same location. Select that and put it in spacefill. Color, spacefill. You can see the inositol hexaphosphate molecule occupying this space in the cleft between the 2 hemoglobin beta chains. And twice select the hemes, color them, put them in wireframe. And the heme groups we can, by the way, the abbreviations for the various ligands are listed on the PDB summary page for each file. You can select the iron, put that in spacefill, red. And now if you look at any one of these heme groups, you can clearly see the iron is out of the plane of the heme. The center of the iron atom displaced a few tenths of an electron. Let's visualize the side chains. Put them in the wireframe a little thicker. Now let's just look at one of the 4 polypeptide chains. if we zoom in on the heme group, clearly see the prostidine over here and the distal histidine over here. Let's try to find out what residues they are. The proximal histidine is number 92, and the distal histidine is 90. So if we select those residues and base fill, clearly see that the histidine is in direct contact with the iron, and the distal histidine is not in direct contact, but it's clearly massive enough to prevent binding of the carbon monoxide molecule in a vertical orientation. So now let's take one of these one of these large membrane complexes. Is the P870 bacterial photosystem. Let's orient this so that the transmembrane helices we're going to delete the water and also a number of code values that are present in the crystal structure. Select ligand, put that in space. So now you see all of the locations of all the different molecules and electron carriers. If I select the chain and by chain, you see that there are 4 polypeptide chains, the peripheral protein, the cytochrome, and the 3 integral membrane proteins in the plane of layer. To save time, by a script that I prepared earlier, and we've put each of the photosynthetic pigments by different color. And let's put the background white again. And if we just show the ligands, you can easily follow the path of the electron from the through the different heme groups in the cytochrome to the chlorophyll special pair, and you can really see. Zoom in on the chlorophylls, you can clearly see that the 2 porphyrin rings and the special pair overlap. The electrons from the chlorophyll special pair to the pheophytin, to the menoquinone, through the iron atom, and to the reversibly bound ubiquinone at the other quinone binding site. As a final example, let's just take a look at double-stranded DNA, and we're going to DNA in the A structure of DNA. This is a structure of a short piece of the A form of DNA. Students are usually very familiar with the B form of DNA, but usually not familiar with the A form. They sometimes find it hard to visualize just from looking at figures in the text. If the can clearly see that the bases are tilted with respect to the helix axis, and the second helix is hollow and filled with water. And you also see that there's a very deep major groove, a very shallow minor groove. With this wireframe, this all allows us to see these features of the molecule, the tilted base. bases and the hollow helix. If we select the backbone, color that on the backbone. The bases are different colors, and the phosphodiester backbone is in the CP colors. And you get further feel for the structure by taking further backbone and the bases and putting them in space fill display. So if we put backbone in space fill, we can see how the chains run around one another. If we do and select the side chains and put this fill, you can clearly see the stacking of the bases in the interior of the helix. And if we select everything and put it in fill, this gives you a very good appreciation of three-dimensional structure of the molecule, the hollow helix, narrow and deep major groove, and wider and shallow minor groove of the double helix. California State University, Long Beach, we find that the students can read instructions in the manual and go to exercises without any assistance from an instructor. The manual is written so that all students have to perform the first few exercises, but each instructor can choose those that they feel are most relevant. By the end of the semester, the students have gained enough competence that they write a short-term paper about the structure of their favorite protein and Jmol images to serve as figures for the paper. So they're not only using Jmol to help them learn about protein nucleic acid structure, but they're also acquiring a skill that they will be able to use in their careers in biomedical sciences. That's
Great.
it.
Thanks.